Suppose I do happen to design different 2-band filter banks. So, first what would a realizable 2-band filter bank look like? We must first put that, we must write that down in terms of a drawing first. So, a realizable two-band filter bank is like this. So, I straight away write it in terms of system functions here. This is a realizable 2-band filter bank provided H 0 z, G 0 z, H 1 z, G 1 z are all rational functions, rational system functions. And of course, H 0 z and G 0 z aspire to be ideal low pass filters with cutoff pi by 2. H 1 z and G 1 z aspire to be high pass ideal filters. With cutoff pi by 2. Now, having put down the structure more generally, we must now ask what is the connection between the multi-resolution analysis and this filter bank that we are trying to design. So, to answer that, let us look at the Haar once again. In fact, let us begin with phi t in the Haar. So, for the Haar MRE, we notice something very interesting. Phi t belongs to V 0, which is a subspace of V 1. So, phi t should be expressible in terms of the basis of V 1. And what is that basis of V 1? It is phi 2 t minus n for integer n. It should be expressible in these terms. It is very interesting. You know, phi t is an element of V 0, V 0 is a subspace of V 1 and the basis of V 1 is again the dilates of phi t by a factor of 2 and their integer translates. So, So, phi t can be expressed in terms of its own dilates and translates. This leads to what is called a recursive dilation equation on phi t. And lo and behold, what is that dilation equation? That is also not difficult to determine. In fact, we can even see it graphically. Indeed, if you recall, phi t looks like this. I have kind of scaled up the drawing, and all that you need to do to get this recursive equation is to notice that this can be redrawn like this. So, it has two components in it, and the first component is phi 2 t, the second phi 2 t minus 1, and the whole thing is phi t. So, we have a beautiful dilation equation which governs phi t. Phi of t is phi of 2 t plus phi of 2 t minus 1, a beautiful dilation equation which governs phi t. Now, let us look at the coefficients in that dilation equation. So, let me put the dilation equation before you once again. The coefficients are 1 and 1. Let me try and call this a sequence, So, if you agree, I will talk about the sequence which is 1 at n equal to 0 and then 1 subsequently as shown at n equal to 1. This is a way of denoting a finite length sequence. The number below the arrow tells us the value at the point of the arrow, and all other numbers tell the value of the sequence at adjacent points. So, this for example means at n equal to 0, the sequence takes the value 1, and at the next point, which is of course n equal to 1, the sequence would take the value 1 2. So, this is the sequence corresponding to the dilation equation coefficients. Let us carry out a similar exercise for the wavelet now. So, let us take the Haar wavelet and let us express the Haar wavelet also in terms of the basis of V 1. And what is our ground for doing so? Let us put it down clearly. You see, recall that psi t or the Haar wavelet, for example, also belongs to V 1. So, it should be expressible in terms of its basis. What is that basis? Phi 2 t minus n for integer n. And again, if we look at it graphically, it is not difficult to do. Graphically, one can sketch phi t actually. And psi t too. So, this is psi t. And you can see the phi t's embedded in it. So, you have one here and you have one there. This is easily seen to be phi of 2 t, and this is easily seen to be minus phi 2 t minus 1. And therefore, we have a very simple dilation equation for psi t. Now, here it is not recursive, but it is a dilation equation all the same. So, dilation equation for psi t. Psi of t is phi 2 t minus phi 2 t minus 1. And once again, let us put down the coefficients of this dilation equation as we did previously. So, the coefficients again would be the coefficients involved in expanding in terms of phi 2 t minus n. As I can see from this dilation equation, the coefficients are 1 and minus 1 respectively at 0 and 1. So, I put that down. Now, things are beginning to make sense and perhaps even ring a bell. Let me put both these coefficient sequences before you once again, and then I am sure it will ring a bell. Look at the dilation equation coefficients for the phi t itself. So, in fact, let me write it down. Dilation equation coefficients for phi t, and let me then put before you the dilation equation coefficients for psi t. So, let us write it down in this for psi t. Does this ring a bell? Yes, indeed. If you look at the impulse responses either on the analysis side or the synthesis side of the low pass filter and the high pass filter, these coefficients are essentially those impulse responses. A minor difference. You see, on the analysis side you have a factor of half. For the moment, keep aside that factor of half. Otherwise, these dilation equation coefficients are just those very impulse responses. Synthesis side similarly, perhaps with a plus minus ambiguity, but otherwise the same. So, we have a very intimate relation which we have seen here. The coefficient sequences in these dilation equations that govern phi t and psi t are actually the impulse responses of the filters. Now, in fact, I will go one step further. We shall now progress to show that if I know these impulse responses, I can go the other way too. So, here I have by serendipity, so to speak, by surprise or chance discovery, come up with this relationship. Now, we will take that serendipity, that discovery further. So, indeed, let us note at the moment that within a scaling factor, if h of n, so to speak, is the impulse response of the low pass filter in question, in the two band filter bank, then essentially what we have is the following dilation equation. So, we will continue the dilation equation. Phi of t is summation on n over the set of integers h n phi 2 t minus n. This is the essential dilation equation for phi. And conversely, if G n is the impulse response of the high pass filter, in the two band filter bank, then we have psi t is summation n over the set of integers G n phi 2 t minus n. So, in the time domain, we have made an intimate relationship. The low pass filter impulse response allows us to expand the essentially phi t in terms of its own dilates and translates, the scaling function in terms of its own dilates and translates. The high pass filter helps us expand the wavelet in terms of the dilates and translates of the scaling function. Once again, low pass filter impulse response, a recursive expansion of the scaling function in terms of its own dilates and translates. The high pass filter impulse response, an expansion of the wavelet in terms of the dilates and translates of the scaling function. Now, we want to go a step further. We want to show that once you have this dilation equation, we can actually completely characterize phi t and psi t knowing the two band filter bank. I shall in the next couple of minutes only give the strategy for doing so, but we shall actually do this in the succeeding lecture, in the lecture to follow. So, let me put before you the strategy that we are going to follow, and for that purpose let me put down the equations before you once again. So, let us recapitulate the two equations we have written. We have this dilation equation relating phi t to its own dilates and translates. What we shall do in the next lecture is to take the Fourier transform on both sides, and noting that we can express the Fourier transform of phi t, or rather phi 2 t minus n in terms of that of phi t, we shall have a recursive equation in the Fourier domain on the Fourier transform of phi. From this, we shall be able to completely characterize the Fourier transform of phi in terms of the discrete time Fourier transform of the sequence H. Having done so, we shall then progress to this dilation equation here, and we will relate the Fourier transform of the wavelet to the Fourier transform of the scaling function effectively. And then noting that the discrete time Fourier transform of the sequence G n can be used to make this relationship, we shall obtain the wavelet from the scaling function. So, it is with these two steps that we shall begin the next lecture. For the time being, let us keep our curiosity alive to see how beautifully we can enmesh the design of the two band filter bank and the design of a scaling function and a wavelet for building a whole multi-resolution analysis. With that note of curiosity and anticipation, let us conclude this lecture. Thank you.